All right, let's do the second problem of the day. This is LeetCode number 662, maximum width of a binary tree. So given the root of a binary tree, return the maximum length or the maximum width of the given tree. The maximum width of the tree is the maximum width among all levels. The width of one level is defined as the length between the end nodes, the leftmost and rightmost non-null nodes, where the null nodes between that would be present in a complete binary tree extending down to that level are also counted in that length consideration. It is guaranteed that the answer will lie in the range of a 32-bit signed integer. Cool. They give us some examples here. So let's get started. I think the most obvious answer, and perhaps maybe not the most efficient, is just to use a BFS or a level order traversal. Including nulls. So this is a pretty standard thing. So for each level, let's see, for each level, add the children or nulls if they do not exist. And then I think what we could do is say pull or pop nodes from the head of the queue until a non-null node exists or is at the head. And then start counting the width between this node and the next non-null node of the layer, or until the layer runs out. I know that there was an example here. I see. Okay, so if there is no node, if there is no other node, then we can, if there is no other non-null node, then we return the previous max width. And the max width is something that we keep track of. In this case, the runtime will be O of n, where n is the number of nodes in a complete tree version of the binary tree. And the space complexity will be O of, let's see, not log n. What is the maximum width of a tree? Of a full tree? Because that would be the most, like, let's assume that it goes all the way down to the base layers. Then that would be, is it 2 to the log base 2 of n? And thus n? Because we know that we will have one node, then two nodes, then four nodes, right? In a binary tree, in a complete tree. So in that case, we have 2 to the height of the tree at the bottom. And since the height is always log of n, then we would have 2 to the log base 2 of n, which is just n. Okay. Let's go ahead and get started with this code, and let's see if it's fast enough. The number of nodes being in the range of 3,000, I think, is less an indication of the runtime and more of an indication of this this answer fitting within 32 bits. So I don't think there's some necessarily some crazy way to do this, where you can fit it within 3,000 inputs, or necessarily that it would be that slow. But let's go ahead and get started. So we'll get started by doing a queue, which will be a linked list of tree node nullables. And we'll add our root in there. Of course, we'll also say if our root is null, then return 0. Because I don't think that there's any width if we just start with null. We'll say we'll have a var max width that starts at 0, and should be fine for now. We'll say while queue is not empty, and we'll say we can use an array deck, right? We will say for I in 0 to q.size minus 1. So this is a for loop, not a for each loop, because we want to, well, actually we could use a for each, right? No, because we'll be modifying it, so we need to, we'll say we'll first say while q dot peak is null, q dot pop or pull, right? So this is just getting rid of the leading nulls. And then afterwards, we'll say for the rest of it, we know that we have our head is probably a null, or a non-null rather. We can say var num nodes added that starts at 0. We can say val front is equal to q.pull. And we can say q.add front.left, q.add front.right. And since this could be null, or at least according to the compiler, it will probably be null, nullable at least. So we need to make sure that we don't accidentally run into a null pointer exception by adding that question mark there. So we add the left and the right. And then we'll say var, let's see, distance between nodes is 0. Distance between nodes plus plus. Let's see. So we go through the layer until we find a non-null value. So we're at a non-null value, and then we start incrementing. We start incrementing if it's not, if it's a non-null. So we can say if front or val front is equal to q.pull. If front is not null, then we do something, or actually rather if it is null, then we can just say distance between nodes plus plus. Otherwise, we want to say q.add front left, q add front right. And if distance var has found next node is false. If distance between nodes is greater than 0, then we want to say has found next node is equal to true. So the idea is that we want to get rid of all the leading nulls, and then we want to start at a particular node. At that node, which is non-null, we will add the left and right children if they exist. And actually q.add null. I think that we need to add nulls as children. We can say val left is equal to front left. Val right is equal to front right. If left is not null, q.add left and num nodes added. If right is not null, q add right, num nodes added plus plus. And the reason that we do this is so that we don't go through an additional layer at the bottom of our binary search tree or our binary tree if we haven't added any of the nodes. Distance between node is that. And let's see. So if distance between nodes is greater than 0, then has found next node is true. And then we don't need to worry about then we can say if not has found next node. So the idea is that if we haven't found the next node, then we want to keep on incrementing. If we have found the next node, then we want to stop incrementing, because then there's no point in incrementing the node counter afterwards, right? Because there may be null values after the node that we found, and we don't care about that. Well, the distance between here, it's between 5 and 9, right? So we don't want the next node, we want the last null, or the last non-null node. In that case, what we can do is that rather than do this, we can say if this is non-null, then we can say if max width, or if distance between nodes is greater than our max width so far, then our max width is equal to distance between nodes. And this will only trigger if we are at a node, another node, right? So we don't need to worry about like this triggering on a value that we don't care about. Then at the end we can say if num nodes added is equal to is less than 2, honestly, then return max width. Because if we only returned one child node, then we know that we can't go further than that. Then we can't go further than no, because we could have potentially like a child node that's 1, and then we could potentially like branch off, like that could branch off like to some stupid amount, right? So actually we don't want to do this. We only want to do this if num nodes added is equal to 0 exactly. Okay, so we start by creating our queue. We assign our root into it. And then while it's not empty, we create 3 values. Actually, we don't need this hasFoundNext node. We initialize a variable for a number of nodes that we've added, as well as a distance between the nodes. We will keep on popping our queue until we get to a non-null node, because the nulls that happen in between, like outside of the range of nodes, doesn't matter to us. Then we go through the actual rest of the remaining parts of the queue. Let's see. Let me think about this actually, because now that I'm thinking about it, do we need to add our number of nodes to the queue? Do we need to add nulls to the queue for our leading nulls? I think actually yes, we should. Queue.add null, queue.add null. And then in that case, we can say val original queue size is equal to queue.size at the beginning. And then we can say original queue size minus 1. Because we only want to iterate through the nodes in this layer before we've added all these children, right? Well, we do want to also get rid of those children, right? So this might be a var. And what we'll do is that original queue size minus minus here. So what this will do is that we get rid of all the nulls, all the leading nulls within our layer count. And then we go through the rest of it, right? Because we don't want to accidentally bleed into the next layer. This is a little bit messy, but anyways, then we go through the rest of the nodes. So by default, we start with the head. We take the front value, it's not null. So we add the left and the right, and we add 2. We set the num nodes added, we increment it twice, so it's 2 now. We add the left and the right into the queue. The distance between nodes starts off at 0, so the max width does not change. Let's see. Actually, what happens if we do have just like a singular node? Does that count as 1 or 0? I assume that counts as 0, right? But we do need to increment the distance between nodes after we've ran our calculations. Queue.size. Okay. So we want to run our calculations afterwards. So then in that case, we've added 2 values. Oh, interesting. Okay, so it starts at 1. Interesting. In that case, then we can do the distance between nodes pre-4. And we do want to increment distance between nodes actually on all of these. Then distance between nodes ++ at the beginning. Because if it's null or if it's non-null, we still want to increment the distance between nodes. So now when we get to here, the distance between nodes is 1 at this point, right? So no nulls to get rid of. We go through this. We go to the front. Front is not null. We add the left and the right. We only add 1. actually, what we could do is that if left is not null, num nodes added plus right is not null, num nodes added plus q add left, q add right, and that should be functionally the same because we need to add the number of nodes added there. So we've added one node. And then we go to the second node in the layer. Now distance between nodes is 2. And then we check the left and the right. Or distance between nodes is now 2, which is greater than 1. So we set max width to 2. At 5, we will distance between nodes is 1, and the rest of the queue is null. Number of nodes added is 0. So then we return max width at that point, which was 2. So that should have worked. Or that one should work. Similarly for these, the number of nulls in between should account for everything. So let's go ahead and run the example cases and let's see how they turn out. This should be num nodes added, not nums nodes added. Yes, that is null, but we know that is null. Or that is potentially null. And we should be able to add null, right? Just a tree node nullable? Does it just not like that? What if we just did that instead? Because I know we can add nulls into there. This queue supports tree node nullable. That is weird. Okay, then I guess we do need to do the full thing then, which is queue.add left, queue.add right, otherwise queue add null. Interesting. Why doesn't the queue like that? So the array deck really doesn't like that nulls are being added then. You know what? Mutable list it is then. And this one would be first. And then we need to do queue.remove at first, or 0 rather, because that fits within there. You remove at 0. The first value is null. Let's see, is there any poll, peak? Cool. I think we've gotten rid of all the queue related logic, and we'll just stick with Kotlin then if that's going to be an issue. Cool, looks like that worked for the most part. That was all 3 of the examples. And let's just do a run with just one, just to make sure that we're not messing around with, or we don't accidentally screw something up. Let's go ahead and throw in a submit, and let's see if we are too fast or too slow, or if there's anything we need to change. Huh. We might run into a TLE, yeah. Okay. This looks like a really big tree. Interesting. Okay. What else could we do then? So a BFS is too slow. Then, if BFS is too slow, maybe we go with a recursive solution then. Maybe BFS is actually fast enough, but this mutable list is just not fast enough. Actually, I do want to check that before I move on to a recursive method. I know that a stack. No. Okay. Yeah, I guess. Huh. We could create like a dummy object in there. No, but a dummy object with. If we use the dummy object, like with literally no values. And we did do that thing with the array deck. Not is empty. If it's not our dummy object, or while it is, then we just create instances of this dummy object. So basically we're just wrapping a null in something different. I wonder if the overhead with the is just that bad. Oh. We can keep that. But we just need to add a dummy object instead. Is dummy object. We can do pull. We can remove that. We can say val value is data class must have at least one. Okay, then we can just get rid of this class then. And oh, it needs to extend tree node. Tree node extend with -1. And I think that works. It might still be too slow. Yeah, it's still too slow. Okay. It was worth a shot, though. It was worth a shot. In my opinion, at least. So let's not bother like even adding that. Okay, in that case, if BFS is too slow, let's try out a DFS method. And we'll say left side maximum is root tree node, and we'll say int, or we'll say left width, which is an int, returns an integer. And then we'll say if root is null, then we return 0. Actually, left width. If root dot left is not null, then we can say val left width. Then we do root or left side maximum on root dot left and left width plus 1. And then we do left side maximum root dot right left width -1, because we go to the right. So if root right is not null, right width, because it could potentially be like a left side after going to the right, that is the maximum. And then we can return max of left width, right width. And then we can say val left width is left side maximum on root and left, or root and 1. So the idea is that we start 1 and then we go all the way left if possible. We increment it and we just increment it and we get the maximum of that side. Otherwise, we go to the right. So let's do a print line on that left width and return that left width. This is just a preliminary check to see like sort of what the width we get, or at least if it's fast enough even in this iteration. Else 0, else 0, or actually else left width. Okay. Is that a left? Oh, I see. Definitely have to see. And then fun right side maximum tree node right width. And this is going to be pretty much the same thing, but just reversing the roles. So right width. Oh, we can do left and right here so we don't accidentally override the values. And we can do the same here. We don't want to accidentally like shadow the input. This is right width. This is right width. you are going to do right width -1 when we go left, and left width +1, or right width +1 when we go right. And we do right side maximum. I think that's all the changes that we need to make. Right width is equal to right side maximum, root and 1. And we want to print line on right width as well. And we want to do a math absolute on left width minus right width. This I don't think is actually going to be completely correct. Let's run it through some previous examples, some base examples, so that we kind of get an idea. I think this one is going to be a little bit iffy. This one is the main one that should be a little bit iffy. Because the left side maximum is 3, right? So 1, 2, 3, but then you are 1, 2. So the output is 1, but in reality we want it to be 2. Is there a way that we could do this? Because it kind of feels like we need the depth as well. Yeah, maximum depth. This one makes... Yeah, because it's also like the stuff in between, right? Actually, now that I think about it, I wonder if the solution is actually using the depth rather than... 1, 2, 3. Okay, so both of these would have a depth of 3, let's say. And, well, we need to figure out if they're on the left or on the right. And even so, the depth isn't the whole story, because if the depth is like here, like they may be on the same level of the depth, but then we also need to know like how close they are to each other in terms of the width. Yeah, I'm honestly lost on this one as well. I wasn't expecting to be lost on both of these problems today, but BFS was too slow, and I think that makes sense because there are just a lot of potential nulls that you encounter, right? So just a lot of nulls to encounter. So that obviously creates a TLE situation. So then we run into DFS instead with the pre-order or some sort of traversal, and then some sort of calculation. That's like sort of, I guess, like the other thing that we can consider. But I'm having trouble thinking about how this would exactly work. I think I'm going to give it like 10 more minutes, and if nothing comes up, then I'm just going to look at the solution, implement it, and then come back. Alright, so turns out it was BFS. I was right the first time, and I probably should have dug a little bit deeper into whether or not I could have further optimized the BFS to not include nulls, because the number of nulls was just absurd, right? Anyways, so the true solution involves a little bit of thinking about how we represent binary trees in an array sense. And what I mean by that is that within an array representation for a binary tree, for any given node index I, its left child will be stored at 2i, and its right child will be stored at 2i plus 1. I believe this is an in-order traversal. So in that case, if we're dealing with an array representation like that, we can sort of leverage that and assume that within a perfect or a complete tree rather, when it comes to something like this, that when we add in our, assuming that we have a complete tree, we will set our left child to 2i as a position as we assume, and we set our right child as we assume it to be 2i plus 1. So we assign individual positions to the nodes within a hash map, and then we use that to actually say, okay, so how many nodes do we expect in between these two values for our leftmost and rightmost, assuming that the tree is complete. So that's pretty much how we get to our solution here. So we create a root, or we create a map, we add a queue, and then we go through in BFS order. If we have a left child, we will add it into our queue as well as add it into our map by getting the appropriate values, which is our current index multiplied by 2. And similarly for our right side, we will do the same thing, multiplied by 2 and add 1. And at the end, after we've gone through our entire layer, we will calculate the maximum width at that layer. And if it is greater than our current amount of max width, then we will set our max width to be that new amount, and then we return it at the end. According to the discussion page, it seems like this solution runs an O of n over divided by O of m time, where O of n is the number of nodes in our list, and m, I believe, is the actual number of nodes within, or the number of nodes within a complete tree. So let's start by just quickly throwing in our test examples just to make sure that we didn't do any regressions and we didn't miss anything. And then let's toss it into our submission and let's see where we end up. Cool, still a little bit slow. I imagine that maybe this mutable list is a little bit on the slow side. We could replace this with, now that we're not using any nulls, we could replace it with any of the JVM data structures, and it would be perfectly fine to run it that way. And that would probably be a little bit faster than removing items from the beginning of a list, right? Because that takes generally order of n time, where n is the number of items in the list. So in any case, I hope you learned something, and I'll see you for the next problem.